Okay guys, let's take a look at today's lesson. We are going to be looking at continuity and discontinuity of trig functions. Okay, so before I start with specifically trig functions, I just want to talk about continuity and discontinuity in general. This is a huge concept in calculus. We actually use this definition of continuity regularly. So what is this? Let's look at it. A function f is continuous at x equals a. This is looking at point continuity at one particular place at a. If and only if these three things exist. Basically our function value, the y value at a exists. The limit at a exists. And those two values are the same. That's the definition of continuity. I'm going to show you an example where that doesn't happen so you can get a feel for what this is really talking about. We won't have this kind of example in this unit, but I just want to further explain just so we kind of understand. So let's say that's A. Okay, so let's say that's what we're looking at, that kind of graph. That's a graph that has a hole in it, right? It has a hole. So does the function value at a exist? Yes, right? It's 3. It exists and it's 3. Does the limit at a exist? Now some of us might be a little disturbed by this, but yes, that limit exists. I know there's a hole there, but the function is trying really hard to get there, right? Really hard on both sides. So it actually does exist. It's 2. And we'll cover this kind of scenario next semester. Okay, I'm just kind of giving you an overview of what this law is telling us, this definition. So does the limit value equal the function value in this case? No, that's a 2, 3 and 2. So 2 does not equal 3, so therefore it's not continuous there. That's the scenario where this shows us that it's not continuous in a spot. For us, working with trig functions, we really are just going to have to work with the first type of discontinuity. That's what we're going to work with in this unit. So there are 3 types of discontinuity. I'm just going to just go through them so we have a big picture. And then we're actually going to just focus on infinite discontinuities in this unit. So let's talk about the 3 different kinds of discontinuities. There's something, so we have an infinite discontinuity. Basically, if we have a vertical asymptote, that creates an infinite discontinuity. What does that mean? That means that this discontinuity, whatever at C, goes on infinitely, right? All the way to infinity and all the way down to negative infinity. It is always, it's like a roadblock, right? We can't get through that. We cannot pass through a vertical asymptote. So that's what we call an infinite discontinuity. We will have these, right? Because tangents got asymptotes, vertical asymptotes, right? Cosecant. We have a lot of trig functions that have vertical asymptotes. So this is really the main one, well, the only one that we're going to deal with in this particular unit. Jump discontinuity, this comes later. These typically are created by piecewise functions where we are, continuous on this side and we're continuous on this side, but right in the middle here at C, there's a jump. I think it's named appropriately, right? We would have to, if we were traveling along here, we would have to jump to get to this other side. So that's what a jump discontinuity is. The last kind of discontinuity is called a removable discontinuity, or a hole. There's a hole. That's like this one that I'm showing right here. There's a hole. So this is the 3rd kind, and again, we won't really work with those until next semester, those types. But we will. We'll work with all 3 types this year. But today, and for this unit, we're just focusing on infinite discontinuities. Okay? Questions in general before we start our examples. Okay, so let's move to our examples. So what we're going to be doing here really kind of is a bit of a review. This should be like, yes, a review. Well, if you liked the graphing unit, this is a great day for you. We're going to be graphing, and graphing is good because you're going to it's a good practice because tomorrow we're going to be doing limits graphically. So it's a great practice. So if you like the graphing unit, you're like, yes, graphing. If you didn't do very well, then you're like, oh, graphing. But it's still going to be graphing. We're going to have to do that one way or the other. So what we're going to do here is two parts. We're going to graph whatever function we're given on whatever interval we're given. We're going to graph the whole function. Okay, then we're going to analyze our graph and determine where, if we have discontinuities, and where they are. Now, this is kind of some free points here, right? Every single discontinuity we're going to be doing in this unit are going to be non-removable. So it's going to ask you, are they removable or non-removable? Well, they're all going to be non-removable in this unit. What's the only kind of removable discontinuity? A hole. And we're not dealing with those with trig. We'll deal with those later. So they are all going to be non-removable. All right. So let's start with our first problem. So we have 2 cosine 3x. We have to examine it on the interval 0 to 2 pi. So we need to graph it on that interval. Let's remind ourselves some basics for graphing. We know this is b, right, that number, and our period is 2 pi over b, so 2 pi over 3 is our period. Let's kind of get this started up. This is our amplitude, right? 2 is our amplitude. So if I'm going to 2 pi, from 0 to 2 pi, let's see, I'm going to have 3 full cycles in there, aren't I? I'm going to go, because my period is 2 pi over 3, so I would go to 2 pi over 3, 4 pi over 3, and 6 pi over 3. So I'm going to have 3 full cycles. Now for the graphing that we're doing in this unit, I'm going to be just a little bit more, I guess, relaxed about the numbers that you put on here than I was. I just need a scale. You don't have to fill in every single spot. But know that to graph, right, if this is a full cycle, we would need to split it in half, and then in half, and in half again, right? We need those locations to be able to graph. This is cosine, so it starts up. So I'd start up and go down. And so my first cycle of cosine would, look something like that. And then I just repeat that in each different, so I need another cycle right here. So I split that in half and in half and in half again. So we plot that one. Then the last cycle, we're going to again split it in half and then half again. So we have the full. Okay, so we've done what they've asked. We've graphed from 0 to 2 pi. Our graph is our evidence of discontinuities. That's what we're using to answer the question. That's why we have to have it. So we look at that and we see there are no discontinuities on that interval. So we're going to say no discontinuities. Since there aren't any discontinuities, there's no question about whether they're removable or non-removable. Right? This question only applies when we have discontinuities. It doesn't apply when we don't. So we don't have anything to evaluate whether we can remove or not. It's just there aren't any. And that's our very first problem. Are we okay with that? So this is really a very good graphing review, and just looking at our graph, to be honest, it's a good graphing review for us. So let's take a look at our second problem. Okay, so we're looking at tangent. It has a normal period of pi, but it's been shifted, hasn't it? It's been shifted, so it's minus pi over 2. That means it's gone right pi over 2, hasn't it? So let's work on that. Alright, so it's gone right pi over 2. So pi over 2. So its little belly shifted, right? This is tangent, so its little belly is shifted over. This 3 just has to do with the stretch, right? How much we stretch it, so it's not really a huge issue for us on this problem. That's not going to determine a difference in discontinuities. It's just going to be how we place the graph. The normal period is pi, so if I started in the middle at pi over 2, then I have to go pi over 2 either side. Right, so my asymptote, my first one would be here, and my next one would be at pi. And this is just regular tangent, so we're just going to graph it like that. Okay, I need to fill the interval from negative pi to pi. So we need some work on the left side of this graph. So I go to negative pi over 2. There's another one. And negative pi. And there's my other. So you can put arrows on it or not. It's just up to you. I'm not going to really be that picky about the arrows, which way you go. So there we have our graph. Let's look at the graph for evidence of the question. What discontinuities are on that interval? Well, it's going to be important for us to recognize whether negative pi and pi are included or not. Right? If they're not included, I'm not going to include them. How do we know whether they're included or not included? With a bracket versus a parenthesis, right? The bracket means they're included. So and I'll write the answer up here. So I'm going to have discontinuities at negative pi, 0, and pi. Those are the three locations on this interval. Then I have to decide whether they're removable or non-removable. Of course, they're going to be non-removable, right? Because they're an infinite discontinuity. Non-removable. And that's my answer. Okay, how are we doing so far? So just a review of graphing really, and looking at the graph and listing discontinuities is all we have on this lesson. Alright, so my last one, it's a little bit more complicated to graph. We got a lot of things going on. Let's see, it's cosecant, so that's a reciprocal of sine. We have a shift, right? We have a left-right shift transformation. It's plus 45 degrees, so that means that it would go left 45 degrees, right? And then it shifted up 3, so we got basically all kinds of things going on. The only thing we don't have going on is a change in period, right? That b is 1, so it's just a regular period of 360. All right, so we're going to go left 45 degrees. So negative 45 degrees, that's where we're going to start. Of course, we're supposed to look all the way to negative 90 degrees, so I'm just going to kind of throw that out there. We've been shifted up 3, and our amplitude is 2, so that would put us to 1 and 5. Right? Okay, so let's work on the numbers here. If my period is 360 and I have to start over there at negative 45, in order to get this space, I'm just going to have to do 360 minus 45, right? I mean, that's how I would find that. And 360 minus 45 is 315. All right, so that gives me that part. So I need all my little locations here, so let me split it in half and then in half again. Okay, so if my full period is 360, that means half would be 180. Right, so 315 minus 180 would give me this value right here. So 315 minus 180 is 135. And then I would need to go 90 degrees on either side, right, just to fill it out. So that would be 45 degrees. Let's kind of hold for a second and let's see what, if we need to get this, what we need. We need to think about the sinusoidal axis would be at 3, and I'm going to go ahead and draw it in. I mean, you don't have to, but I'm going to go ahead and draw it in, and the little shadow thing, remember the little shadow graph we used to draw? I'm going to go ahead and do that just so we're clear. So this is cosecant, which is sine, and it's negative, so it will go down. Right, so I would start here, and I would draw the little shadow guy going down like that, right? And then it would come up like that. Do we remember where the asymptotes are? Where are the asymptotes on cosecant? Let's say where sine crosses the sinusoidal axis, right, or touches it. So I'm going to have an asymptote right here. I'm going to have an asymptote right here and right here. I'm going to have those asymptotes. Of course, that's our main goal with this lesson, is to find the discontinuities. Okay, now I need to go out to 90 degrees and over to 360. So that would just kind of go like that. So we're not going to have any asymptotes action out there. So let's draw the little pieces of cosecant. So it would be like this, and it would be like that. So we're going to be required to draw all of the parts right through this in this entire interval. So I don't know, this one's going to be something like that, and that would be something like that. Okay, so I'll pause here for a second. Are we okay with the graph? So now I need to just put, so I don't have any asymptote action out here by the -90 or the 360. I really just have these three to list. So x is, this is discontinuous when x equals -45, -45 degrees. And then at 135 degrees, and then at 315 degrees. And are these removable or non-removable? Non-removable, non-removable. All right, and that is our last problem. Okay, any questions we need to look at? Okay.